Last week we already in chapter 4, the state machine, finite state machine, and we have looked at the more type FSM for finite state machine, and we have looked at the example, right? How to design the finite state machine, the more type finite state machine for simple application. So this application is to regulate the car speed, the vehicle speed, where when the where we have the uh, fixed measurement time. We measure the speed of the car in fixed interval. For example, every 5 seconds we measure the speed of the car, and if the speed is uh, exceeding the speed limit that we have set, uh, and if it exceed for only a short time, a very short time, so the controller will not reduce the car speed yet. It will wait for the next measurement, and if it's still exceeding the speed limit, then it will send the signal to the car controller to reduce the uh, speed of the car. All right. So we have looked at this already last week, and this is the state diagram of that controller. All right, the finite state machine, and this is the block diagram. So the block diagram is actually quite universal for finite state machine. If you look at other finite state machine, the structure of this block diagram is pretty much the same, except that the output is different. So, for example, in our previous example, the output is Z, is what is Z. So, Z is the signal to regulate the car speed. If Z is 1, means that you need to reduce the car speed. If Z is 0, means that nothing, do nothing. And we have one input here, which is the W input. So this W input is the input from the speed measurement device, right? So if W equal to 1 means that the speed is exceeding the speed limit. If the W equal to 0 means that the speed is not exceed the speed limit. So in general, the structure of FSM is like this, except that how many input that we have. In this case, we have only one input, and only one output as well. Is that all right? So if for other application, for example, you may have more than one input and more than one output, but the structure is pretty much the same. Yeah, the difference is that how many output that you have and how many input that you have, right? Uh, so in the finite state machine, for more type finite state machine, so the structure will be always like this. You have the combinational logic before your state register. This because state register your flip-flops. In our case, we see that because we have three state, three state. So the number of flip-flop must be more than one flip-flop. All right. Because if you have only one flip-flop, you can only represent two states. So number 0 represent the first state, and number 1 represent the second state. But if you have more than uh, two states, you need more flip-flops. All right. So for example, we have three now, three flip states. So you need to have at least two flip-flops, because the first one, the first state, you need maybe you want to represent using 0 0. All right, the second one is 0 1, and the third one is 1 0. All right, 1 1 don't have any state. So But if you have four state, how many flip-flop you need? You need two flip-flop, right? 0 0 0 1 1 0 1 1. But if you have five or more, all right, so you will need more flip-flops. If you have five, you need at least three flip-flops, right? 0 0 0 until flip-flop number 5 is 1 0 0. Okay, so in this case, you you will need two flip-flops, all right, and you need the combo or combinational circuit, all right, as the input to the flip-flop, and the state, the state of the finite state machine, all right, is this. The output of the flip-flop is the state, the current state or the present state of uh, the finite state machine is uh, small y. Yeah, so is the input to the combinational circuit here to generate the output signal. All right, and you will always have the feedback. All right, this is the feedback signal from this Y to the combinational circuit here. It will always like this. Yeah, it will always like this. So your job is to design what is inside this box and inside this box. So we have learned already last week how to design that, where you need to have this and the state assign table where you uh, represent the state as the digital representation. For example, state A you represent with 0 0, state B you represent with 0 1, and state C 1 0. And this is the next state. Means that uh, if we are in state A, when the input is equal to 0, where we should go. All right. So in this case, exactly based on the state diagram that we designed. All right, when W equal to 0, so we should remain at state A, exactly this, right? So when W equal to 0, we stay at state A. And when W equal to 1, we go to state B. All right, so this is B, 0 1 is B. And the output for state A is Z equal to 0. Okay, and for state B, when 0 1, so we state B is represented by 0 1, and when W equal to 0, we go back to A, and when W equal to 1, we go to state C, and the output for state B is Z equal to 0, and for state C, when W equal to 0, we go back to A, and when W equal to 1, we remain at C. All right, and the output for state C is Z equal to 1. And again, because this is digital, all right, so you need to have all combination. Yeah, so the last combination, which is 1 1, that not represent any states. So this one is don't care. All right, we put don't care for this. Don't care. And for that, we can generate this signal. All right, y1 means that this. Yeah, how to generate? You can use the KMAP to generate the signal for y1 and also y2. All right, and also z. All right, and at the end we will have this circuit. Right. So this is how we design the circuit for the finite state machine. But if you look at this, the process is quite troublesome, time consuming. Take into account that if we have more state, if we have three state like this, it's still simple, easy to generate the Boolean equation to generate the circuit. But if we have, for example, 10 states, so the process is not that easy, right? But we are lucky because we have a Verilog where uh, we can describe the behavior of the circuit by based on the truth state, not truth table, the state diagram here. All right. So last week we have learned how to write the code, for this. So first thing is that you need to uh, have this, So to draw this is easy because you have two flip-flops, all right? So you draw two flip-flops and you draw the combo here, the box like this, and you have one set, and you have input W to the combination logic like this, and you have the feedback from here to here. So this is your general uh, functional block diagram of your circuit, and you try to write the code for this, for this, not for this, not for this. All right, for this using behavioral modeling. All right, so uh, we know the behavior of this circuit based on this. All right, so how to do that? First thing first is the easiest one step to start is that we describe this flip-flop first, right? So to describe this flip-flop is quite easy, straightforward. So this is how, yeah. So the flip-flop is negative edge reset and positive edge clock. Here, if reset equal to 0, so y should be equal to a. What is a now? Our a is actually 0, 0. All right, means that state 0. All right, state 0. And if not reset, if reset equal to 1 or reset is not active, so what is y? Small y. Small y should be this. Should be capital Y, right? So that we get the flip-flops, right? So this code here will create two flip-flops for you, where the output of that flip-flop is small y and the input is the capital Y, just exactly like this, yeah, output and the input. And now you can define the combinational circuit for the next state combinational circuit. So where is the next state combinational circuit? Should be the first one here. See? All right. So how to do this? Yeah. So the input of this circuit will be this W, Y1 and Y2, small y1 and small y2, and the output will be Y, capital Y1 and capital Y2. All right. So you can use the case statement and see we use the always block where the input is W and Y, small y. All right, and Y here we have 2 bit. All right, and please change this to 1 to 0, just like what we did last week. 1 to 0, not 2 to 1. All right, if you use this, you will have problem when you do your design equators later on. All right, so look at this, how to define or describe the next state circuit, combinational circuit. All right, so if case y, if w, case y, if a in state a or 0, 0, if y equal to 0, 0, all right, means that for this one, if this signal equal to 0, 0, what should be this? And of course, should be depend on W as well. So if this one is 0, 0, 0, 0 here means A, state A, all right? So if this equal to 0, 0, so what should be this? So we know already this is the next state, represent the next state. So the next state will be B or A, 0, 0 or 0, 1. All right. So 0, 0 or 0, 1 depend on W. So the code will be, if we check the W, if W equal to 1, so the output of that combinational circuit will be B or 0, 1. All right, B is 0, 1. Okay, but if W equal to 0, the output there should be 0, 0 or A in this case, 0, 0. See? And if we are at state B or 0, 1, if the output of the flip-flop or the state of the finite state machine is 0, 1 or B, 0, 1 or P, so if W equal to 1, so we go to C exactly, 1, 0, the output of the next state combinational logic is C or 0, 0, 1. And if W equal to 0, we go back to A, right? And here, if we are in C, if W equal to 1, we remain at C. And if W equal to 0, we go back to A. And for others, the last one, we don't care. All right. So this will give you this circuit. All right. And the last one is the Z. All right. The last one is the Z. So Z, we can Z is equal to 1. We can use data flow modeling. Z is equal to 1 when Y is at state C. When Y equal to, we can use this, or you can use always block. Always block. All right. If Y equal to C, means that if we are in state C, so Z equal to 1. All right. Okay, so this is how we describe this using query law. And this is, remember, this is more type state machine. And now we will look at another type of the finite state machine. This is the Mealy state machine. Okay, so what is the difference between Mealy and more state machine? This is the difference. Number 3. Mealy type machine. In Mealy type machine, the FSM, the output value are generated based on both the state of the circuit and the present value of its input. All right, or in other words, if you look at the general structure of the Mealy state machine, you can see that the Z here, the output of the finite state machine, is not only depend on the present state value, but also depend on the input. All right, but for more type, you don't have this line. All right, Z will only depend on the output of the flip-flop. But for Mealy, Z is not only depend on this, but also this. That is the difference. Right, let's go back to look at the Mealy. Do we have that? No. Yeah, Mealy, you see, sorry, more, you see, Z here, the output Z is only depend on this input, this signal, which is the output from the flip-flops. Z is not connect directly to W, but for Mealy, you can see Z also receive the signal from W. All right, so that is the difference. And also, when we have this, the state diagram also different a little bit. All right, and how to design the state diagram for the Mealy type finite state machine. So this is how. So using the same example, so we can see that here we have state A. All right, state A. We start with state A, and when we reset or when we start, we are in state A, and the different style of drawing this finite state machine as compared to the more is that we can see that the output Z here is not in the state. All right, when we look at the more type, the output is in the state. All right, because the output is only depend on the value of or the present state, the present state. All right, so the output Z is inside the state, but for Mealy, the output is not in the state. All right, the output is here outside in between transition of the state. All right, for example, if W equal to 0 when we are in state A, when W equal to 0 means that the car speed is not exceeding the speed limit, so we still in state A. All right, we still remain at state A, and from the state transition the output is here at the state transition Z equal to 0. All right, but when W equal to 1 means that the speed limit is the car speed is exceeding the speed limit, W equal to 1. But remember, if one time exceed the speed limit, so Z is still 0. All right, but we need to go to B. All right, and the next measurement, for example, when W equal to go back to 0, so we go back to A, and Z still equal to 0, means that that is maybe the false signal. All right, so go back, and 1 again, you go to B, and if go down to 0, go back to A. But if W equal to 1, for the first measurement, we go back and go to B, and if the next measurement, W equal to 1, now Z equal to 1 already. So we can see that this is two consecutive measurement. We have W equal to 1. All right, 1, 1. So Z equal to 1 already in B when we have the transition here. All right, so 1, 1. We need to reduce the speed here. Z equal to 1. And still, if still 1, W equal to 1, yes, we need to reduce the speed. And if still 1, we need to remain at B and Z equal to 1. And if if W go down to 0 after that, then we go back to A. So this should be our state diagram for the Mealy state model, Mealy state machine. So now what is the difference between the two? Yes, we know that the first difference is that the input for more the output for more the output is inside the state. For Mealy, the output is in at between the state transition. So whether we remain to A at A or go to B, so that will be activated during the transition. All right, and the next difference is that we can see that before this, when we use more state machine, we need 3 states, right? And now when we use Mealy, we only use 2 states. So for some application, Mealy state may give you a more in more optimized circuit. I mean, lower cost circuit, right? So because when you have 2 state, means that now you need only 1 flip-flops, right, to represent your state. All right, 0 and 1. Okay, and the process of generating the this signal and this signal is pretty the same with the more state machine, where you need to have your state table and the state assigned table, and from this you generate the signal y and also signal z, and this is very simple actually for Mealy state diagram. All right, so you try to do this on your own and try to generate this circuit. So this circuit is of course based on this equation, this Boolean equation, where y is actually equal to d and equal to w. So we see, all right, so this is y, capital Y, all right, and z is w and small y. So this is small y and this is w, z. And we see here, you see z here, the output is depend on the present state of the finite state machine, and also depend on the input, which is w, exactly. All right, so this is Mealy state model or state machine, and the Verilog code is pretty the same. All right, but now you have state, only two states, A and B only. All right, to define the sequential circuit is pretty much the same. The only difference is that our y now is 1 bit instead of 2 bit. For more, now we have only 1 bit. All right, but the code is the same, only that the size of y is now 1 bit. All right, so if reset equal to 0, so we are at state A. All right, or y input here is equal to 0. State A is 0. Okay, but if not reset, if reset equal to 1, in this case, why reset equal to 1 is not reset? Because reset here we use net edge reset, means that this reset is active low. So when the reset signal is equal to 0, so we should reset the flip-flops. All right, and if not reset, so y the output is y here is this, capital Y here. All right, exactly. And now we want to describe the next state logic and also the signal Z. All right, so if when we are in state A, all right, use case y, all right, so y equal to 0, small y equal to 0 or A. So if w equal to 1, all right, so z should be equal to 0. Z equal to 0, so means that this one. If w equal to 1, z equal to 0, and the next state will be b. That's why we have the next state equal to b. But if w equal to 0, so we should remain at a. If w equal to 0, z equal to 0, and we the next state should be a. So exactly when w equal to 0, z equal to 0, and the next state is a. And when we are at b, if w equal to 1, so z equal to 1 already, and the next state will be remain at b. And if w equal to 0, z should be equal to 0. Yeah, if w equal to 0, z should be equal to 0, and we will be at state a. Exactly. All right. So very easy for describing the finite state machine using Verilog. Yeah. So after this, we will not do this. All right. So this is just for knowledge, for you to appreciate that when we have Verilog, we can describe the circuit using behavior of the circuit. All right, rather than uh, deriving the Boolean equation, which is a very time-consuming task, especially when your circuit is big. All right, just imagine if you have more than 10 states, to derive this is, yeah, you can, but it's time-consuming, right? So you can use the Verilog to describe the behavior of your finite state machine. All right, so later on we will use this behavioral modeling to model the state machine. So after this, the toughest job is to derive the state diagram, all right, from the specification. So we no need to do this, all right. When we have this, we can straight away uh, write the code for this. So the difficult job is that to derive the state diagram. All right. For example, if you have the specification, how to derive, yeah, how to draw the state diagram based on the state specification that you have. All right. Now let's look at this example. The second example, uh, so serial adder. So before this, in chapter, we are in chapter, what chapter is this? Chapter 4, right? So before this, in chapter 2, we have designed a parallel adder actually, where we add the numbers parallelly. We have A for example 4-bit, B 4-bit, and we add parallelly actually, right? So let's look at this. So before this, what we did is to add the number is something like this. For example, we have two number A and B, and we have 4-bit number 0010 000001. We add, yeah, using the full adder, and we have 1100, and this is done parallel in parallel, right? And the good thing about this is that we can get the result very fast, right? Very fast, right? Because if this is our full adder circuit, so we have A 4-bit here, and we have B 4-bit here, right? And we can have S, right? Straight away, all right? But the problem is this one, not the problem, just the issue or the drawback is the cost, right? We see that we need, if 4-bit, right? If our adder is 4-bit, so we need how many 1-bit full adder? So we need 4 1-bit full adder, right? If our adder is 8-bit, so we need 8 1-bit full adder. If our adder is 16-bit, so we need 16 1-bit full adder. So the circuit is getting bigger, bigger, and bigger. All right, depend on the size of our data, right? And when you increase the size of your circuit, of course, you increase the cost of your design, all right? But in some application, all right, where the speed is not that important, uh, that we can compromise, all right? And but we want to lower the cost. Maybe we can add the number in serial, right? So most of the things, most of the design, we use serial. For example, in communication, all right, when we want to send data, we don't send in parallel actually. We send in serial because of the cost, right? You see the communication protocol, right? The I2C, the SPI, the UART, serial communication, all right? The internet, we send the data, we communicate in serial, not parallel. Means that if our data is 64-bit, we not send 64-bit at a time. We send bit by bit, right? So that will reduce the cost a lot. Yeah. So now actually we can add in serial, means that we add one by one, bit by bit. All right, 0 plus 1, save the result, get the result. All right, for example, we have the uh, we learned already, right? The data must be in the register. We have two register. The first one is register A. Second one is register B. So the number is I use the same number 0010. This is 0001, and we send this out 0 first and send number 1, and we have what we call a serial header or uh, an header here, an header, full header, and the output from this is also the register. This is too big. Okay, right. So we send 0 and 1 first, we add, and the answer should be 1. S should be 1, and carry should be 0 or whatever. So, and the result is 1 here, and we shift, yeah, we shift this 0 to this, yeah, we shift to the right, and now we add 1 to 0 here, 1 0, the second bit, yeah, when we shift to the right, and also we have this, and this here also shift to the right, and get the new result. We shift, and we shift until we have all value, and then get the result in the output register, right? Using this only one header. All right. So you can see that the speed, yeah, is maybe 4 times smaller, slower as compared to the parallel header, but you only have one bit header here. All right. Uh, the cost here is lower. So this is 4 bit. If you have 8 bit, you still need only one header also here. If you have 16 bit, you only have one header. You still have one header here. So the cost is not that increased much, only that the size of the register is bigger, right? So you see here, you save the cost, yeah, by using the by doing the operation, the add operation in serial, rather than in parallel. All right, but the question now is how to design this adder, right? So we can use finite state machine to do this, right? How to do that? So we can have something like this, where we need to understand, or we need to know uh, the process, the operation of adding in digital. All right. And of course, we have learned this before, so should be no problem. So, but let's go back to this where we have the truth table for the full header. So we will have C in, we will have input A, input B, and we have uh, C out, and also we have sum, right? And the input will be all the combination for 3 bit. So we have 8 combination starting from 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and plus 1 is 1, 1, 1. And the output for this should be 0, 0. This one should be sum 0, no carry. Sum 1, no carry, 0. This one also the same. This one you have sum 0 and carry equal to 1. This one you have 0, this one, this, and this one should be this, and this one should be 1 and 1. All right. So this is the truth table. Now, how to use this to design the state diagram? Okay. So, of course, we need to have the first state, right? So just draw the first state. Okay. So let's name this as G or A or P, whatever you want. In this case, G, and in this case, I will give you the Mealy type, Mealy FSM. Okay, and we have the second state. Call it H, where at state G, we have, when we add number, all right, there will be no carry in, and no carry out. At state H, you have carry in and you have carry out. All right. So when we are at state G, we have input A and B. All right. So we have two input. And also carry in. All right. When we add, yeah, if no carry in and no carry out, so we need to stay at state G. So look at the output here. When we add number, all right, when we add number, when there is no carry in, so must be this this for condition. Oh, sorry. This for condition when there is no carry in. All right, and we will stay at state G when there is no carry out. So should be these three condition, right? These three condition. So we can say that if, yeah, this is A and B equal to 0, 0, the output S should be 0, S. And remember, for Mealy state machine, the output is at the state transition. All right, so when A and B equal to 0, 0, so S should be equal to 0 here. And when there is no carry out, we should remain at G. And here, when 0, 1 and 1, 0, S should be equal to 1 and we remain at state G. So means that if 0, 0 or 0, 1, we should remain as G also. But S equal to 1 now. 1, 0 also remain at G equal to 1. But 1, 1 here, you have carry out. So when you have carry out, you cannot stay at G. You need to go to H because you have carry out. So when 1, 1, you go to H. All right. So if A, B equal to 1, 1, so your S should be equal to 0, and you go to state H. All right. So now for state G, you have all the possibilities from 0, 0 to 1, 1. 0, 0, you stay at G. 0, 1, also you stay at G, except that your S is 1. 1, 0, you also stay at G. And 1, 1, you go to H. All right. So that will be the first state. And the second state is when carry in equal to 1, or this part. Yeah. So we look at the second part, which is this one. All right. And here, when we look at this, all right, when the input is 0, 0, AB 0, 0, so there is no carry. All right, there is no carry. So if no carry, we should go back to G. All right, so 0, 0, and the output should be S, should be 1. And we go back to state G, all right, because there is no carry out. So you need to go back to G, because our specification is said that if no carry out, we should go to G, or should be in G. All right, but when 0, 1, all right, 0, 1, because you have carry equal to 1, so you should remain at H, remain at H, and the output should be 0. And also, yeah, you can look at here, these three, all these three we have the carry, so we should remain at G, right? So we have 0, 1, where the output is 0, 1, 0, the output is 0, and 1, 1, the output is 1, I mean S, right? This is AB. All right, so this will cover or represent all the values for A and B, right? 0, 1, 1, 0, 1, 1, and 0, 0, right? So the state diagram, the final state diagram should be this. Okay, so now we have the state diagram already. We can write the code for this. Okay, so let's write the code for this using the vectors.